recording to my YouTube channel. All right, Chemistry 3101, where we left off last class was talking about hydroboration oxidation. It's a two-step process in which we do an anti-Markovnikov addition of water across a double bond. You see the conditions are here. It is a two-step process. The first step is borane and THF, which is a complex. I told you that sometimes if you do MCAT study guide materials or ACS study guide, sometimes instead of BH3THF, they write B2H6, which is called diborane, and it does the exact same thing. And then the second step is hydrogen peroxide and sodium hydroxide. I also told you that you didn't need to know this mechanism. But anyhow, what you do need to know is that not only is it an anti-Markovnikov addition of water in terms of the regioselectivity, but that we get syn addition. And syn addition means that the hydrogen and the hydroxyl are added to the same face of the molecule. If the hydrogen and the hydroxyl were added to opposite faces of the molecule, we would call that anti-addition. And we will discuss anti-addition a little bit today with some other reactions. But we don't see that in hydroboration oxidation. So not only is it anti-Markovnikov in terms of regioselectivity, but in terms of stereoselectivity, we get syn addition. Okay, so with all that in mind, we went over all the background last class. And where we left off was looking at a problem. This one here. It says predict the products for each of the following transformations. So we have a double bond. We're doing a hydroboration oxidation. If I highlight this carbon in yellow and this carbon in blue, let's say, could anybody tell me which one of these carbons is going to take the hydroxyl? Keep in mind, this is an anti-Markovnikov addition. It's going to be the yellow one that's going to take it, right? The yellow one. Okay, so remember, Markovnikov is the rich get richer. So if we look at this compound, this carbon has one hydrogen. So if it was Markovnikov, then this carbon would be taking a hydrogen, but this is anti-Markovnikov. And so it's not the rich getting richer. It's the carbon that's richer in hydrogens is going to take the hydroxyl. So it's the yellow carbon that's going to take the hydroxyl. And so we end up with one stereocenter in this case. So if we draw the final product, right, we draw the final product, we end up with one stereocenter, right? We have the hydroxyl here. And so what that means is that we're going to get a pair of enantiomers. We're going to get one enantiomer where the hydroxyl is coming out. And then we're also going to get another enantiomer where the hydroxyl is going back into the page like this. So we get a pair of enantiomers. Now keep in mind, there was also a hydrogen added here, right? We added a hydrogen here, but the stereochemistry is irrelevant because that is not a stereocenter. Okay, it's not a stereocenter because the pathway going this way and this way is identical, so not a stereocenter. So we just leave those hydrogens out. The syn addition is irrelevant for that hydrogen. All right, we get a pair of stereoisomers here, a pair of enantiomers. All right, for the next one, we get no chiral center. So let's try it again. If I highlight this carbon in blue and this carbon in green, could anybody tell me which one of these carbons is going to take the hydroxyl if I'm doing an anti-Markovnikov addition of water? So again, anti-Markovnikov, right? It's the green one that's going to take the hydroxyl. Exactly. So we're going to draw 1, 2, 3, 4, 5 carbons. We'll put the hydroxyl out here, and we're done. And remember, there's no chiral centers here, so no chiral centers, and so we don't have to worry about we did have to worry about regioselectivity, but we don't have to worry about stereochemistry. All right, there we go. So that covers hydroboration oxidation. A student asked me a question the other day, said, how much material do I need to know from this chapter for this quiz? And that's a question that's very difficult, I would say impossible for me to answer. But just to put this bug in your ear, a reaction like this, hydroboration oxidation, this is going to be part of the content of this course from now until the end of organic chemistry 2. Hydroboration oxidation is never going to go away. We always need a way to add water in an anti-Markovnikov fashion. So let's move on to our next section, which deals with catalytic hydrogenation. And remember that this chapter deals with addition across pi bonds. And so what are we adding when we're doing a hydrogenation? Well, the name is kind of given away here, hydrogen, right? So we're adding hydrogen. And we know that hydrogen is one of the molecular elements or the diatomic elements that exists as a molecule in its pure form, right? We know hydrogen, nitrogen, oxygen, fluorine, chlorine, et cetera, et cetera. So we have hydrogen, H2, adding across a double bond. So what's going to happen is when we take an alkene and we treat it with H2, and I'm just going to color code it in red here, what we're going to do is we're going to add one hydrogen to one of the formerly sp2 hybridized carbons, and we're going to add another hydrogen here. So we end up converting an alkene to an alkane, right? Converting an alkene to an alkane, so hydrogenation. And what's interesting about this reaction is that it requires a metal catalyst. If you don't use a metal catalyst, the reaction takes really high pressures and really high temperatures. And you can imagine that messing around with hydrogen gas at high temperature and high pressure is pretty dangerous, right? Because hydrogen gas is explosive. And so the metal catalysts that you're going to see a lot of the time, there's three of them: platinum, which is the one you see here, palladium, or nickel. Okay, and if you're wondering, well, which one do I use under which circumstance? This is one case where you can really use any of them, and I would be okay with it. Okay, they all have the same, or they can all affect the same transformation, the conversion of an alkene to an alkane. All right, so there's no regioselectivity to be concerned with here because both of the atoms that we're adding are identical, right? They're both hydrogen, so that doesn't really have any effect on regioselectivity. However, the reaction is stereospecific. It's stereospecific in that we only see syn addition. So we only see the two hydrogens being added to the same face of the molecule. And there's a very good reason for that, which I'll show you in just a second. So let's say you had this compound here, okay, and you were doing a hydrogenation. You're going to get a situation where both hydrogens are either going down, right? There's syn to each other, right? Syn addition, or they're both going up. Those are the two possibilities that you're going to have, all right? So you would end up with this pair of stereoisomers. So syn addition is what we see for hydrogenation. And the reason why we use a metal catalyst, and again, the metals that we can use are palladium, platinum, or nickel. The reason we need those metal catalysts is because it lowers the activation energy and it actually changes the pathway to a certain extent. Now, I'm not going to ask you about, how does it affect the mechanism, because the mechanism of this reaction is kind of tricky. But the idea is that if we lower the activation energy, the reaction is going to be faster, right? We know that going all the way back to General Chemistry 1. And so here is the mechanism. And if you're thinking, well, that doesn't look like a mechanism, where are the curved arrows? There aren't any curved arrows in this mechanism, are there? Right, so what happens, and I'll try to explain it here the best I can, if I redraw this molecule here, so this is just 2,3-dimethyl-2-butene, right, what happens is the alkene kind of is moving around, okay? And what happens is that you add hydrogen to your catalyst. So this is the surface of the metal catalyst right here. So let's imagine this is your platinum metal, right? These are just individual atoms of platinum, okay? So what happens is when you treat the metal with hydrogen, the hydrogen atoms break, okay, or sorry, the hydrogen molecules, the bonds break, and we end up adding all these hydrogen atoms to the surface of the catalyst, okay? So they're adsorbed on the surface of the catalyst. So then what happens is that the alkene kind of comes down and it lands, on the surface or by the surface of the catalyst. And you can see that since it's approaching one face of the catalyst where all the hydrogen atoms are, it stands to reason that the hydrogen atoms are going to be added right to the same face of the molecule, right? They're going to be added like this on the same face. And that is why we get a syn addition. Now, it's easier for me to explain this with my hands, but I don't think I need to switch over to my camera because I've never asked a student a question about this mechanism in my life, and I'm not going to start now unless it was something in the homework. But the idea is that the alkene lands down kind of like a UFO, right, approaching the surface of the Earth, right, and then the hydrogens go up just onto one face of the alkene, which would be the bottom of the UFO. Give me a thumbs up if that makes some just rational sense to you at all. Okay, and again, I'm not going to quiz you about this mechanism. There aren't any curved arrows in it. Okay, so there you go. Yeah, so that's the mechanism of hydrogenation. And just one word of caution that David Klein puts in our textbook, which is, good food for thought. He says, okay, well, just because it's syn addition doesn't mean you're always going to get a pair of enantiomers. What if you had this compound here? Now this compound would be 1,2-dimethyl cyclohexene. If you did a hydrogenation on this compound, you could end up with the hydrogens going on either face of the molecule, but then you end up with a compound that's got a plane of symmetry in it. And so this is a meso compound, right? So that means that this compound, right, is identical to this compound. There's no difference between the two. So it's just kind of a word of caution of just because it's syn addition doesn't mean you're always going to get a pair of enantiomers, right? Okay, so anyhow, just keep that in mind. And I feel like my students are pretty good at identifying meso compounds. They're pretty good at recognizing them and remembering that. So just something to think about. We're not going to cover the section on homogeneous catalysts, excuse me, but what we've covered, okay, what we cover in this class in 3101 are heterogeneous catalysts. So the metals that we use, platinum, palladium, or nickel, those don't dissolve in the reaction mixture. They actually stay undissolved, so it forms a suspension when you stir the reaction mixture. But there are homogeneous catalysts, meaning ones that do dissolve in the reaction medium, in the solvent. And the way that they do that is they make these what we call ligands, and that's something that you would have covered hopefully in your chemistry. So that would have been covered a little bit in chemistry 1411, ligands. It renders the catalyst soluble. And if you're wondering, well, why would I even care about that? Well, it's because with some of these homogeneous catalysts, you can do a stereoselective hydrogenation. So meaning, or enantioselective is what I should have said. You can make one enantiomer over another. But you can see that I skipped this section. Why? Because it's not covered in the final exam. It's not covered in any of the quizzes. It's not covered in ACS, so don't worry about asymmetric catalysts, okay? Don't worry about chiral catalysts. Again, we're going to skip this section. We will talk about this briefly. We are going to talk about this section briefly in chemistry 3111, okay, in the section of amino acids, but it's not covered in chemistry 3101, so don't worry about that. All right, so these are the kind of questions that I expect you to be able to answer with respect to hydrogenation. So could anybody remind me, when I do my hydrogenation, do I get a syn addition or an anti-addition? It's not a trick question. Right, thanks, Hannah. Exactly. So if we're doing a hydrogenation, it's a syn addition. That means that both hydrogens are going to be added to the same face of the molecule. Well, the thing is with the first one, when we add two hydrogens, we get no stereocenters whatsoever. So if there's no stereocenters to worry about here, let's just add our hydrogen atoms. So let's just scribble them in here. So we end up making this alkene into an alkane. And for the next one, we actually do end up making a stereocenter in this one, don't we? So if we do our syn addition, the way we would do this, or the way that I would do this, the way I would draw this, since we have a hydrogen atom coming down here, like this, in the molecule, is I would kind of imagine this molecule kind of looking flat. Like imagine you're looking at the molecule kind of like that, like it's as if it was flat. So I'm going to start by drawing the bond. I'll highlight this carbon in red and this carbon in blue. Okay, so I'm just going to draw what's there, but I'm going to break the pi bond because we break the pi bond when we do our hydrogenation. So we get our bond between our red carbon and our blue carbon. Okay, we get our ethyl group going in the back. So this is the ethyl group. That's that group right there. Then we have the hydrogen coming out in front. Okay, and that's this hydrogen. Then we have a methyl group going in the back like this. And we have an ethyl group coming out in front like this. So if you're wondering, well, where are the hydrogens that are being added? So let's just color code it here. We have our H2 molecule, so we're going to have one hydrogen on this face, and it's syn addition. So, and if you're looking at that molecule and you're saying, well, that's not the most stable conformation, that's irrelevant. Okay, it's still the right answer. Okay, even though it's in an an eclipsed conformation, it's still the correct answer. So there you go. So a syn addition is what we end up with in this reaction. And you can see that there's only one stereocenter in this compound, right? The only stereocenter is the one at the blue carbon. And so you could just say, well, I end up with this. You could just draw the compound like this. So we have 1, 2, 3, 4, 5, 6. So we have 1, 2, 3, 4, 5, 6. And then on the carbon, 1, 2, 3. 6. So 1, 2, 3. So 1, 2, 3. Then we could say we've got a stereocenter here, and then we would say plus enantiomer, and that's it. All right. So does that make some sense to everybody, the way I drew that? Hopefully you can see what's going on here. So all I did was count the carbons like this: 1, 2, 3, 4, 5, 6. So I went 1, 2, 3, 4, 5, 6. Again, carbon 4 is not a stereocenter. You see it's got 2 hydrogens attached to it, but carbon 3 is a stereocenter. It's got a hydrogen, a methyl group, an ethyl group, and all of this attached to it, right? A propyl group. There you go. So that's all we get, is we get 2 stereoisomers, 2 enantiomers, and that's it. All right, there we go. So that's a little bit about catalytic hydrogenation. So let's move on to the next reaction, which is halogenation. And I know you know what the halogens are, right? You know the 4 halogens. We have fluorine, chlorine, bromine, and iodine, right? And I drew them as their diatomic, since these are diatomic elements, I drew them in their molecular form. Well, the thing is, when we do a halogenation reaction in organic chemistry, we never do it with fluorine and we never do it with iodine. And the reason why is the reaction with fluorine is too violent, and the reaction with iodine is the opposite. It's too slow. So the happy medium is somewhere when we do either chlorination or bromination. But I would say, you know, based on the two of these, we look at bromination even more than chlorination, and that will become abundantly clear as we move further in the course. Just give me 1 second here quickly. All right, so take a look at this example here. So if you take ethylene, so this is ethylene or ethene, they both mean the exact same thing. Ethylene is the common name. Ethene is the systematic name. So if we do a chlorination or a bromination, so again, a halogenation, what we do is we add 1 halogen to each one of the sp2 hybridized carbons. So this is one of the key steps in making polyvinyl chloride, which, has anybody ever purchased a polyvinyl chloride pipe or PVC pipe to do any plumbing projects at home? Okay, cool. I always ask that, you know, and I figure that there's a couple people who know what PVC is, right? Anyhow, so PVC pipes, which are commonly used in plumbing. And just to put the bug in your ear, if you're wondering, you know, when do we cover polymers, right? When do we cover organic polymers? That's covered at the very end of organic chemistry too. It's actually the last chapter we do in the entire course. Anyhow, so if you're wondering, you know, well, you're probably thinking, well, first of all, I don't have to worry about regioselectivity with halogenation because I'm just adding 2 of the same element. It's either 2 chlorine atoms or 2 bromine atoms. And like I said, fluorination is too violent. Iodination is too slow. And so when it comes to regioselectivity, there's nothing to consider. But when it comes to stereoselectivity, here's the answer. The answer is anti-addition. So if you're starting to think, oh man, this is getting tricky, you know, I got the hydroboration, which is syn addition. I've got the hydrogenation, which is syn addition. Now I've got the halogenation, which is anti-addition. And the answer is, yeah, it does get a little bit tricky. Okay, so you have to kind of straighten these things out in your mind. But one of the great things about halogenation is once you see the mechanism, it becomes abundantly clear why it is an anti-addition. So just something to think about there. So in this case, if we were to brominate cyclopentene, so let me just scribble the name in here, cyclopentene. When we do that bromination, we end up with a pair of enantiomers. So these are enantiomers. You know something? I don't always read the textbook before I come to class. You know, I've read the textbook many times. And this morning I was actually looking at it while I was having my coffee, and I noticed that in this section, he has a little note next to it. And it says something, and did anybody notice this note where it says, you know, sometimes students have a difficulty differentiating between the 2 compounds, these 2 enantiomers, and they'll think, well, they're the same compound. So if you're in that boat, and hopefully you aren't, but if you are, one thing that you could try doing is making a molecular model of both of these, and you compare the 2, and you'll see how they are very different from each other, or at least they're different. Okay, maybe I shouldn't use the word very, but they are certainly different compounds, these 2 enantiomers. All right, anyhow, so if you're wondering about the mechanism, well, here it is. Actually, sorry, this is not the correct mechanism. This is kind of an introduction to the mechanism. I wish they wouldn't put incorrect mechanisms in the textbook because this is not the correct mechanism, but he puts it here to prove a point. So let me show you what he's getting at here. So bromine itself is a nonpolar molecule, right? You've got Br2, and I know you can all draw the Lewis structure of Br2, which is just this. So both of those atoms have the same electronegativity. There's no dipole in the molecule. Good. Okay. But the thing is, if you remember the definition of polarizability, it's the ability of an electron cloud to distort itself, and it increases as the size of an atom increases. And so bromine, Br2, the molecule is actually polarizable. And so if a nucleophile approaches bromine, it creates a temporary dipole in it, right? Like, right, it will repel the electrons and push them to one side, and then you have a partial positive on the other. And so that results in a force of attraction between the nucleophile and the bromine because of that temporary dipole. And so you might think, well, maybe I'll just have a nucleophilic attack, right, from my pi bond, and then a loss of leaving group, and I end up with a carbocation, and then bromide can just come in here, and I'm done. But the problem with this mechanism, so this, and again, I'm not a fan of putting mechanisms that are wrong, so let's just put a big X through it, okay? There we go. That is an incorrect mechanism. And the reason why is this. It's because you can't form a carbocation. Because if you formed a carbocation, that would mean that this bromide could attack from either face. It could attack from the front. It could attack from, oops, it could attack from the back. And so you would get a mixture of syn and anti-addition. But we only get anti-addition. And so this mechanism is incorrect. The correct mechanism would never happen this way. And okay, this is just further rationalization showing you that you can't have a carbocation. I guess red was the wrong choice here, so I'll use green. We'll put an X through that. So the correct mechanism actually involves 3 curved arrows in the first step. We get a nucleophilic attack loss of leaving group occurring at the same time, but we also get a pair of electrons forming a bond here with the ring so that we end up with a 3-membered ring that we call a bromonium ion. See that we have, let me zoom in on it for you guys. Look, we have a bromine, right? And then we have 2 carbons in the ring. It's a 3-membered ring called a bromonium ion. And that is the key to explaining why we only get anti-addition. Because when the bromide comes in from the back, it's going to attack via backside attack. We only get backside attack, right? It's going to come in from the bottom here, which is the least hindered face of the molecule. And so after it does, we end up with anti-addition, right? The result is that we get anti-addition because of backside attack. And so the key really, I remember learning this back in the 90s, is the first step, that there's 3 curved arrows in the first step. We get nucleophilic attack, that's this step here, right? Loss of leaving group, but then we form the 3-membered ring, the bromonium ion, with this curved arrow here. So the key is the bromonium ion. Give me a thumbs up if you're like, yeah, bromonium ion, I see it. I understand why the backside attack would occur, because this face is going to be more hindered, so it's going to attack from this face, and that's why I get anti-addition. Well, there you go. That's the whole mechanism. I'm going to put this in here. I'm going to put a red star on this one, everybody. I think this is a mechanism that is crucial for organic chemists to know. It's not a long mechanism, but I think it's a very important mechanism for you to know. All right. Can I just say one more thing about the bromonium ion that I didn't? Is, we haven't looked at a lot of 3-membered rings, and we're actually going to see, a few 3-membered rings along the way in this class. In fact, today we're going to talk about an epoxide, if you read the chapter. But you can imagine, like with my molecular model kit, you remember the one that I was using in the stereochemistry chapter? I can't even make a 3-membered ring with my Feezer models. You can't do it. It'll break the models. And so the idea is that a 3-membered ring usually is very strained and it wants to open up. So 3-membered rings are oftentimes susceptible to nucleophilic attack. Anyhow, just something that I wanted to share with you before we move on from there. So in terms of stereoselectivity, the reaction is stereospecific, right? We only get anti-addition. And so what's going to happen now is that the stereochemistry of the starting alkene is going to govern what kind of products that we get. And let me just, if you're not awake, okay, let's stop right here. Take a drink of coffee. Okay, I don't have any left. I drank all mine. Take a drink of coffee and wait. Check this out, because I want to tell you, my friends, if there's one thing that the book loves to quiz you on, It's anti and syn addition with cis and trans alkenes and trying to get you to make sense out of all this. So I want to show you something very carefully here. If you have cis 2-butene and you do an anti-addition, you end up with a pair of enantiomers, right? You end up with these two compounds. So these are enantiomers of each other. But check this out. If you do the bromination on the trans alkene, so trans 2-butene, you might think, well, I'll get a pair of enantiomers. No, you don't. It looks like you might have a pair of enantiomers, doesn't it? But if you rotate this bond 180 degrees, what do you see? You actually end up with, so this compound here, it doesn't look like, that's not the way we draw meso compounds, is it? We don't, I never have, okay? But you have to know that if you rotate that bond, that is in fact a meso compound. And if you're sitting there thinking, going, oh, sugar, that means I'm going to have to rotate bonds and look at conformations just to be 100% sure. The answer is yeah, for sure. Okay. And I'm going to try to look at a few of these problems with you either today or next class, just so we can kind of help straighten these out. I've asked these on quizzes many, many times. Okay. And so syn and anti-addition on cis and trans alkenes. The textbook has a bunch of questions about it too. So in a few minutes, we're going to cover dihydroxylation, and we learn two types of dihydroxylation. We learn syn and anti-dihydroxylation. So that's, again, why the textbook, the author of the book, ACS, MCAT, they just love to quiz people on this because it's a way for an instructor to ask more than one question in one question, if that makes any sense. You're thinking, that's not nice. Well, it's just the way it is. It's something they love to test students on. Anyhow, let's see if we can make some sense out of these problems here. It's bromination. I don't even have to ask you. I know that you know that it's anti-addition. So we're going to get one bromine on one face of the molecule and the other bromine on the other face of the molecule. I'm going to give you 1 second to look at it. Just going to grab my notes here quickly, just to make sure I don't leave anything out. I don't think I have. Wilkinson's catalyst. Yep. All right, so let's take a look at the first one. Could anybody tell me in the first one, are we going to get a meso compound or a pair of enantiomers in A? That's all my question is, and it's not a trick question. It's not a loaded question. Would we get a pair of enantiomers or a meso compound if we do an anti? Exactly. Thanks, Sean. Yeah, we get a pair of enantiomers. So if you're wondering about it, all Sean is saying is this: is he's just saying, like, look, you're going to have one bromine going down. You're going to have one bromine coming up. So what that means is that the methyl group on the top has to be up, and the methyl group down here has to be going down. And you're going to produce the enantiomer as well. So let's draw the enantiomer. So you just do this. We're going to have the methyl group going down. We're going to have the bromine coming up here. There we go. Not my best artwork. We're going to have the methyl group coming up here and the bromine coming down like that. So these are a pair of enantiomers. Enantiomers. All right. I shouldn't put an exclamation point. Everybody good on that? Does that resonate with everybody? And I'm not just saying that for a thumbs up. If there's a question, don't hesitate to stop me, okay? All right, let's try the next one. In the next one, we're going to form two stereocenters, aren't we? Right, we're going to do it again, form two stereocenters. So in B, let's just draw it out here very carefully. So we've got 1, 2, 3, 4, 5 carbons in the main chain. So what I'm going to do is I'm going to put one bromine going up here, and I'm going to put the other bromine going down like this, okay? And that means the methyl group would be going up. And then I'm going to reverse those bromines. So I'm going to have this bromine going down. There we go. I have the methyl group going down and the bromine coming up like that. What do you think? So again, we end up with a pair of enantiomers. Okay. Now, even if you're watching this video, or if you're in the class with me right now and you're thinking, you know, I've got this maybe 70% of the way, I would say that's good. I'd say that's great, because to get the last 30% in your brain, you're going to have to try it yourself, right? You're going to have to try it a few times to make sure that you're confident on it. So the first thing that you would look for, Hannah, if you have a meso compound, is you just want to rotate it and look for a plane of symmetry. but it would be impossible to have a plane of symmetry in this compound, right? Because if you look at this carbon and this carbon, the two carbons that are stereocenters, they have a different connectivity, right? For example, right, this carbon had, the green carbon has a methyl group and this one has an ethyl group, so it would be impossible for it to be a meso compound, okay? They'd have to have the exact same attachments, and then you'd have to figure out, is it a pair of enantiomers or is it a meso compound by rotation? But Hannah, we're going to look at a couple examples of that today, okay? I just have to cover the content on dihydroxylation, and then I don't promise things to people, but I promise you we'll look at a couple of examples of it today, okay? Yeah, I think, trust me, it's important. In my old notes, one of my old notes, it might even be in my binder here somewhere, but I had a whole page just devoted to that one time. So yeah, I'll definitely cover that with you in some more detail today. All right, just a few more reactions to end out the chapter. The next one is halohydrin formation. If you go back here, something that I know you guys are very astute, and something that you've probably noticed, has anybody noticed that a lot of times in this class, do you remember in chapter 7 I brought up solvents, DMSO, acetone, HMPA, and then you're like, okay, you brought them up, they showed up in a few questions, but in most questions you don't even have them in there, right? There's not even, I don't even list a solvent in here, and I didn't come up with a question, the author of the textbook did. So a lot of times in organic chemistry we leave out the solvents. And if you're wondering, is the reaction just done in pure bromine? The answer is no, definitely not. This would probably be done in something like dichloromethane as a solvent. And don't worry, don't stress about that one bit. But the idea is that it's in some kind of solvent that isn't going to cause any reaction, okay? It's in something that's just, there to, as a medium to stir the molecules to get them to move around and collide. But sometimes we do reactions in solvents that are going to participate in the reaction. And so if instead of just doing the bromination, right, like we did in the last section, just putting Br2, in this section, what we're going to do is we're going to change it. We're going to do a bromination, but we're going to run the reaction in water, okay? And so what happens is water is the solvent. Now, the bromine is a reagent. Okay, so I'll ask Sean this question. I just keep bugging you, Sean. Sean, what's going to be present in a greater amount? The solvent, water, or the reagent bromine? And anybody can answer the question. I'm just giving him a hard time. Yeah, exactly. There's a hell of a lot more, pardon my language, water than there is bromine, right? Because water is the solvent. And so the idea is this, because what happens is that the pi bond in your alkene, so the pi bond in your alkene, yes, it's going to react with bromine to form a bromonium ion, right? But instead of a bromide coming in and doing the nucleophilic attack, this doesn't happen. Why? Because there's so much dang water that actually water comes in as your nucleophile, and you make this intermediate oxonium here. So after that undergoes a deprotonation, we call that a halohydrin, okay? So a halohydrin, it's kind of a weird name, the halohydrin. But check out the next step, okay? So we form the bromonium ion. So again, that's the reaction between, it's my black pen, here we go. The reaction between the alkene and bromine to form the bromonium ion. But then water acts as our nucleophile. Why? Because it's the solvent, right? There's just so much of it. So it comes in, acts as a nucleophile. You do a proton transfer, and you end up with a halohydrin. Okay, so that's the first part. And if you make one with bromine, you call it a bromohydrin. If you do it with chlorine, it's called a chlorohydrin. I don't know. Anyhow, but okay, so there's two things that we have to consider. We have to consider the stereoselectivity, and you can see that it's anti-addition. Okay, so that answers that question. It's anti-addition. I probably have it listed in the slide here, the thing about the stereoselectivity. Maybe I don't. But let's just write in here, halohydrin formation. Let's highlight this, and we'll put a little mark here, and we'll say anti-addition 100% of the time, no exceptions, okay? It's always anti-addition. Now, here's where it gets interesting. What about regioselectivity? Because you're adding a bromine and a hydroxyl. So where does the bromine go? Where does the hydroxyl go? The answer is, I'll just tell you the quick answer right now. The answer is the hydroxyl will go on the more substituted carbon. Now, obviously, in these examples, both carbons are identical. But check this out. If you look at this example here, right, the carbon in red is more substituted than the carbon in blue. The carbon in blue has hydrogens attached to it. The carbon in red has no hydrogens attached to it. So what I told you was that the answer is this. Let me get my highlighter out. The hydroxyl adds to the more substituted carbon. And if you're thinking, well, I'm going to remember that the halogen adds to the less substituted carbon, what you have there, that's fine too. I just find it easier to remember that the hydroxyl goes to the more substituted carbon. And it's all based, and you're like, well, what's the rationale? Give me a reason why. It's all based on this. It's based on forming the bromonium ion. Okay, so in this case, you'd form a bromonium, okay, and the water, and it's counterintuitive, isn't it? It's going to attack the more hindered carbon and crack this ring open. And you're probably looking at that going, this subject, why would it do that? You taught me 10 times in chapter 7. You must have mentioned it 100 times that nucleophilic attack would occur at a less substituted carbon. Why would it attack here? You know what? That would be a great question, and there's a good reason for it. Let me show you the answer. I'll just tell you right now, most students just kind of memorize it, but the rationale, it does make sense. It attacks, it says the attack happens at the more substituted carbon. So let's highlight that. More substituted carbon. Here's the answer. I have it on right here, okay? Why would it do that? It's because when the water attacks, okay, and you break the bond here between the bromine and the carbon in the ring, the positive charge passes from the bromine, right, and then you get to the product. It goes from the bromine down to the oxygen, but the pathway is that it passes through this carbon, right? The positive charge kind of travels through that carbon that I have in blue, through this one here, okay? And the key is that the more substituted carbon is going to be more comfortable taking on this partial positive charge. That's the reason why. Give me a thumbs up if that makes some sense to you. You're like, yeah, I get it. So it's like lightning passing through something, like a current, right? And the charge is passing through the more substituted carbon, which is more capable of taking on that partial positive charge. If you're wondering, are we ever going to see something like this again? The answer is yes. You do see another example of something kind of like this in organic chemistry too. And it's actually towards the beginning of the class. So if you take that with me in the fall, you'll see it in the alcohols chapter. But anyhow, I digress. So where were we? Okay, we were talking about halohydrin. So let's get a little practice here. I'm going to redraw this compound. That's not big enough. So let's do something like this. Okay, and we're treating this with bromine in water. So what I'm going to do is I'm going to highlight this carbon in yellow and this one in red. Could anybody tell me which one is going to take the hydroxyl, the OH group, hydroxyl group? And it's not a trick question or anything. Yes, thanks, Sarah. It's the yellow one, right? Because it's more substituted. So we could get some practice drawing the mechanism. I know you didn't ask me to, but whatever. Let's just take a quick gander at it here. So first thing we're going to do is we're going to form our bromonium ion. Remember, it takes 3 curved arrows to do that. Let me eliminate this highlighter. There we go. All right, so we get our nucleophilic attack, loss of leaving group, and then we tie in here to make the 3-membered ring, the bromonium ion. So I'm going to draw that very carefully. So we're going to have the bromonium ion kind of pointing up like this. That's positive charge. Oops, that's not very good. Positive charge on that bromonium. All right, then we're going to have a methyl group on this carbon. So if I highlight this carbon in red, that's this one. If I highlight this carbon in blue, that's this one. And on the carbon in blue, we've got an ethyl group coming down here. And then we've got a propyl group. So 1, 2, 3, like that. And now our water molecule is going to come in and it's going to attack from the bottom face of the more substituted carbon and crack that ring open. And after a proton transfer that I don't have room to draw, so I'll just put another arrow here, what you're going to end up with is this. So we end up with the carbon skeleton looking like this. We've got the bromine coming up like this. We've got the hydroxyl going down like this. And then we've got the ethyl group coming up like this. And I'm just going to write plus the enantiomer. So there you go. a little bit of halohydrin. So remember, this guy here is called a halohydrin. More specifically, this one would be a bromohydrin. And can I just tell you one more funny thing? We're going to take a short break now, but you probably won't find this funny. But the halohydrin, there's not really a lot of uses for the halohydrin until organic chemistry 2. So it's in this chapter. And if you're like, well, why do I have to learn it now? Because it's in this chapter because this is the alkenes chapter, right? And it's a reaction of an alkene. But I promise you that we will use the halohydrin for something cool at the beginning of organic chemistry 2. Okay, I'm going to teach you how to use it to make a new functional group that we cover in chapter 12. So anyhow, but in this class, we use it more to test your ability to remember mechanisms and regioselectivity and stereochemistry. That isn't funny, is it? All right, let's take a short break, and then we're going to come back, and we're going to take a look at dihydroxylation. So just by way of an introduction, it's the only reaction that we look at anti and syn addition. So we look at anti-dihydroxylation first, and then after that, the book teaches you about 6,000 ways to, I'm kidding, but it teaches you a whole crap load of ways to do syn dihydroxylation. And then after syn and anti-dihydroxylation, then we learn, a lot of students like this reaction. It's called ozonolysis. And there's a really cool skill builder. I think it's skill builder 8.8 in the textbook. If you want to look at it during the break, it goes over a really fun way to kind of solve these ozonolysis problems. So that's what we'll cover after the break. And that is actually the last reaction in the chapter. Okay, this is the one in 8.13. And after that, we're going to get into some synthesis.